All right, so let's get started with chapter 4. The title of chapter 4 is going to be Chemical Equilibrium, and that is already a qualitative difference with chapter 3, which was Physical Equilibrium. In chapter 3, what we were really interested in is the stability of a pure substance between two phases, or the stability of a mixture in two phases, liquid and gas, a mixture of liquid and gas, and so forth. But notice that until now, we actually have not talked about chemical reactions at all. This was just water and hemoglobin, and we're just looking at the physical properties of that. What we're actually going to be moving towards today is going to be chemical reactions. Okay, so what happens when you put glucose 6-phosphate and fructose 6-phosphate, and you just put the isomerase enzyme that is going to drive the reaction, right? How is the reaction going to take place? Okay, chemical equilibrium is actually a fundamental concept in the life sciences. As a matter of fact, what happens is that in the life sciences, you have that life works really hard to avoid equilibrium. Okay, equilibrium essentially represents death in the life sciences, and we're actually going to see why with just a simple example. Okay, so let me pull that up here, and we're going to be looking at here the concentrations of ions in and out of a cell, right? So you guys have studied this in many other courses. This is your cell, a very cartoonish representation of a cell, and you guys know that for the most part, okay, you have concentration of sodium ions in the outside that tends to be much larger what you have in the inside. And if you think about potassium ions, it's exactly the opposite way, right? You have that generally, there's much more, many more potassium ions in the inside than in the outside. Clearly, this is a situation of non-equilibrium, right? If there was nothing special about this membrane, the concentration should be the same outside and inside. But what we know is that, through evolution, our cells have these potassium and sodium pumps in the membrane, these proteins, that are actually working really hard to make sure that you never reach equilibrium. As a matter of fact, if you ever reach equilibrium, if the concentration of sodium ions outside and inside were the same, you'd be dead. That's what it is, right? As a matter of fact, this is so important to us that in neurons, okay, 2/3 of the energy expenditure of a neuron are invested in making sure that those gradients are there, that you don't have equilibrium of concentrations outside and inside the cell. Okay, as we know, these gradients actually control neurotransmission to the brain and so forth. Okay, so this is actually pretty important. But I guess notice that right here is actually a clear example that in the life sciences, there's always situations of non-equilibrium. So studying what equilibrium represents is going to be very interesting for us in order to be able to understand this type of processes. All right, so we're going to get started here with a very simple derivation for a chemical reaction of which we're actually quite familiar. Okay, so suppose that we're looking at the reaction A to give B, and this reaction might be reversible. Okay, this reversibility is the first time that actually appears here in the entire semester. Until now, we simply were considering chemical reactions going from A to B, but you guys remember from neurochemistry that most reactions are reversible to some extent. Okay, and that's what we're going to start to think about here. This is just a generic chemical reaction, but notice that we could actually use a biochemical reaction, say glucose 6-phosphate isomerase into fructose 6-phosphate, as it happens in your glycolysis. Okay, it's exactly the same deal here. All right, so let's come up here with mixture of this, and we're going to do the following. Okay, so suppose that I have some N sub A moles of A and some N sub B moles of B. Okay, notice that these are now not two different phases, these are two different substances. Okay, and this is your initial state, and your final state is going to be something like this. You're going to have that a little bit of A has reacted to generate a little bit of B. Okay, so what you have is that you still have A and B right here, but now your moles are going to be N sub A minus differential of N. A tiny little bit of A has disappeared and reacted, and then that means that the number of moles of B that you're going to have is a little bit larger. Okay, N sub B plus differential of N. You have formed a little bit of B. The question here is, well, what is the change in Gibbs energy for the reaction, and whether we can actually say that this reaction is spontaneous or not. We know that the criterion for spontaneity that we like to use is the change in Gibbs energy. All right, so we're going to take this initial and final step, calculate what the Gibbs energies are, and then be able to determine whether this process is spontaneous or not. All right, so we will calculate here, we will calculate delta G, but since this is a differential step, we're going to just be using here a differential of G, which is, again, an infinitesimal change. This is simply going to be the Gibbs energy at the end minus the Gibbs energy at the start of the reaction. Okay, let me actually write that a little bit higher up so that we can write below differential of G is simply going to be G of F minus G of I. Alright, so let's try to write here what the Gibbs energy would be at the start of the reaction, or at this point of the reaction, and then at the end of this process. All right, the initial one is going to be fairly simple. You're simply going to have that, well, there's two species that contribute to the Gibbs energy, A and B. The contribution of A is simply going to be the number of moles of A times the contribution per mole of A. Okay, so that will be the contribution of A to the total Gibbs energy. And the contribution of B will be exactly the same, but with just the B parameters here. Yep, this should not be mystifying to you. We've seen this before. Okay, but notice that when we have mixtures, we don't refer to those molar Gibbs energies as molar Gibbs energies. We refer to them as chemical potentials. That's what we do. Okay, so this, we really are renaming it as this mu sub A, and we're simply renaming this as mu sub B. Okay? All right, what happens at the end? Well, at the end what happens is that, well, the number of moles that you have is now going to be equal to N of A minus a tiny little bit that has reacted to B times the chemical potential of A, right? And what you have is that the contribution of B is going to be N sub B plus differential of N times the chemical potential of B. All right? We just have to take the difference between those two values, and then we'll figure out what the change in Gibbs energy is. This should be very familiar to you, right? We did something very similar to this at the start of chapter 3, but instead of having A being a reagent and B being a product, what we actually had is that A was ice and B was a liquid. But the setup was essentially the same, right? And the difference here is that we're now not naming the molar Gibbs energies as molar Gibbs energies, but chemical potentials. Remember that in the case of phase equilibrium, we use that type of result to learn that the phase that is more stable is the one with the lowest molar Gibbs energy. Okay, that's what we did this. All right, let's start to see what this is. So you take the difference of those two, and you're going to find that this differential of G is simply going to be equal to differential of M mu sub B minus mu sub A. Okay? Of course, that's not what it is. Mu sub B minus mu sub A. Here you go. That's good. All right, if this happens to be negative, then the process will be spontaneous. If this happens to be positive, then the process will happen to be not spontaneous. All right, under what conditions is this going to be spontaneous? This has to be negative. What that means is that the chemical potential of A has to be larger than the chemical potential of B. This is where we now understand the full meaning of the word chemical potential. Notice the significance of this. Is that the chemical potential of A is larger, then the reaction of A to B will happen. Yes? You guys understand that? If the chemical punch of A is larger, then A will be able to drive the reaction towards B. That's where the meaning of chemical potential really comes into play. You guys understand this? Yes? All right, so that's where it comes from. All right, we're going to take this just one more step and say that differential of G over differential of M is going to be equal to, yes, mu sub B minus mu sub A. Okay? And this is what we call the reaction Gibbs energy. This is simply going to be equal to the chemical potential of product minus the chemical potential of reagent. Okay? This is extremely powerful to you. It's going to be very extremely powerful. And I'm going to try to show to you why that is. Okay, until now, what we actually have said is, the way that we have phrased this type of problems has been as follows. Okay, suppose that you actually have here that we're not looking at the reaction of glucose 6-phosphate turning into fructose 6-phosphate. Let's talk about a reaction that we might have looked at. For example, H2, which is a gas, plus 1/2 of O2, which is a gas, to generate H2O, which is a liquid. Okay? And up to test 2, a question that I could have asked you in the test is to say, well, is this reaction spontaneous at 1 bar and 298 Kelvin? And the way that you actually answered that question was by doing the following. You went to the tables and said, well, I can find here what delta Rg is, okay, by just calculating what the change in enthalpy in the reaction is, minus T delta Rs of the reaction is. Yes, that's what you did. If this number was negative, the reaction is spontaneous. If this number is positive, the reaction is not. Also, this number is actually related to the maximum non-expansion work that you can do, and that was another set of problems. Yes, everybody understands this? But there's actually a huge limitation to this way of doing things that you guys did not appreciate at the time, and we're going to see what the limitation is. When you go to the tables to calculate the change in enthalpy, the change in entropy, okay, the tables are actually have a keyword in them, and the keyword is not 298 Kelvin. Both of them have that. There's actually a keyword that is very important there. What was the keyword? Does anybody know? They tell you blah blah blah. Enthalpy formation for a species at 208 Kelvin, or blah blah blah. Molar entropies at 208 Kelvin. What is the word that we're missing here?
Pressure.
Standard. Standard. And what does standard mean? Standard means 1 bar of pressure. Notice the challenge with that. What that means is that everybody is at 1 bar of pressure. Okay, so that one has to be at 1 bar of pressure, that one has to be at 1 bar of pressure, and this has to be a pure liquid. That's what standard means. But notice that this is not very useful, because what happens if you're actually working in a situation in which this is half bar, and this is 0.25 bar, and this might be not pure water? How do you actually calculate delta Rg? What you were doing until now, again, is simply calculate something that is called standard. That. Okay, so for a biochemical reaction, this is even more shocking. Okay, so for example, we did those type of calculations when we were looking at the combustion of glucose. Okay, where the reaction is going to be C6H12O6, which is a solid, plus 6O2, which is a gas, gives 6 CO2, which is a gas, plus 6 waters in the liquid phase. Ladies and gentlemen, when you were calculating delta Rg for this reaction, you were actually doing that at the standard state. And again, notice how the shortcomings of that. That requires that the pressure of oxygen is 1 bar and the pressure of CO2 is 1 bar. When you do this in your mitochondria, are those pressures 1 bar? There's just no way. No way, right? You have very tiny concentrations of O2. Maybe in your lungs, that concentration falls to about 0.1 bar. By the time that you get to the mitochondria, that concentration is much more than that, yes? And certainly, you're not generating CO2 at 1 bar of pressure. You just generate a tiny little bit of CO2 in your mitochondria. This is not what that means is that, as a matter of fact, while this is useful, it's actually a very limited applicability, right? Because again, it constrains you to be at the standard state, okay? What we're going to be learning now to do is to actually be able to do that at any conditions. Now we're going to be able to calculate delta G at conditions inside your body without having to be at the standard state, okay? And the reason that we're going to be able to do that is because notice that what we actually have here is the chemical potentials. And what we have done really hard in the last 2 lectures is work how these things depend on concentration, right? So now we're actually going to say, well, we can actually use this at 1 bar or half bar or 25 bar. We know how this thing changes with pressure. And that is actually going to allow us to come up with a way of calculating the change in Gibbs energy as you move along from a reaction to from a set of conditions to the next. You guys understand that? Yes? Okay, so that's kind of framing the discussion. All right, let's introduce here a graph that is going to try to illustrate what we're trying to do here. All right. Just following up here with the shortcomings of this type of expression, suppose that we recovered here the glucose 6-phosphate to fructose 6-phosphate equilibrium. And let's say that I tell you, well, suppose that we start with 1 molar concentration of glucose 6-phosphate and 0 molar concentration of fructose 6-phosphate. And the question that I have for you is, well, do you guys think that that reaction is going to be spontaneous when it happens inside your body? 1 molar and 0. And you will say, well, yes, it's actually the second step in glycolysis, so yes, it's going to happen. But what happens is actually if I tell you, well, suppose that the initial concentrations are half molar and half molar. Will this reaction continue to be spontaneous? Now we actually don't know, right? What happens if I tell you, suppose that the initial concentration is 0.01 molar, and this concentration happens to be 0.99 molar. Are you still going to be able to drive glucose 6-phosphate to fructose 6-phosphate? And many of you will say, probably not, right? Notice that whether the reaction is spontaneous or not depends on how far along the reaction you are and whether you have a lot of these or not, right? So somehow we actually have to take that into consideration, right? And it turns out that the different chemical reactions have different sort of behavior. Okay, so what we're going to be plotting here, I'm actually going to be using the graph that is in the book, is a plot of the Gibbs energy versus the progress of reaction. All right, which is very nicely exemplified here in your book. All right, so we go to the first line in your book, chapter 4, and let's take a look at these graphs and see what they try to mean. This is how the Gibbs energy changes according to the progress of reaction. When you're here, that means that the reaction has not started, you only have reagents. And when you're here, it turns out that the reaction is 100% complete. Okay? And we're going to take here case C to start with. All right, question for you. I actually did my lecture point here. All right, so we're going to be starting up here. And we're going to be going towards that direction, okay, towards products. Okay, and again, remember this is the Gibbs energy. If I ask you, well, is the reaction of A to B going to be spontaneous if you start here? The way that you would do this is say, well, tell me how the Gibbs energy changes for that step. And you'll say, well, the Gibbs energy actually drops, okay, which means that I'm going to be losing Gibbs energy. That's good. That will be a delta G that is negative, and that will be spontaneous. So this means that I'm right here, A to go to B will be spontaneous. Suppose that we're right here, so now you have that about 33% of the reaction is complete. Okay, is the reaction still spontaneous? Then you will say, well, if I move into that direction, the Gibbs energy still falls. So right at the point, I'm still going well. I can, the reaction to go from A to B, still spontaneous. But suppose that you actually get to this point right here. And you find, okay, well, what happens to the Gibbs energy if you decide to continue to go to products? Now the Gibbs energy increases, which means that delta G is positive. In that case, the reaction is not spontaneous. Well, the reaction A to B is not spontaneous, is the backward reaction B to A is spontaneous. Well, if you try to go back to reagents, you find that the Gibbs energy actually increases, so you can't go there either way. Once you reach this point, you essentially reach an equilibrium, the reaction terminates. You can't make more progress either to reagents or towards products, right? In this case, what this means is that the reaction is about 90% complete. If you have started with 1 molar of glucose 6-phosphate and 0 molar of fructose 6-phosphate, the reaction will stop when you get 0.9 molar of 0.9 molar of fructose 6-phosphate and only 0.1 molar of the reagent. It's 90% complete. Okay? Well, let's suppose actually that the reaction follows this line, B. In that case, what you actually can see is that, well, if you're starting reagents, well, the reaction can proceed until you get to this point, which is about 50-50, right? When the concentration of those two are equivalent, then you actually reach an equilibrium and you can't move anymore. And there are some reactions that actually go overlap, right? You start right here and say, let's try to go to products. You try to go to products, but all of a sudden when you get to the point, it turns out that going to products is not spontaneous. The reaction stops. It's only about 10% complete. Okay? So various reactions are going to have various steps of these different profiles. And what we're actually going to try to do is come up with a way to compute whether at any point in the reaction the step will be spontaneous or not, right? So you can have concentrations that are here, or there, or there, or there, and you'll be able to figure out whether the reaction is spontaneous or not. Okay, so for example, think about glycolysis. Okay, glucose burning to generate CO2 and water. Well, notice that if you try to compute whether the reaction is spontaneous or not after you have eaten breakfast, the concentration of glucose in your blood and your mitochondria is going to be pretty high, right? And that will give you a different value for the spontaneity of delta G as if you're actually famished and there's very little blood sugar in yourself, right? So those things actually change, and the Gibbs energy and spontaneity of the reactions also change. What we try to do here, we're going to be trying to do here, is try to come up with a way to compute exactly what delta G will be at any concentration that you might want, and that's why this expression is more that powerful. All right, so let's see how we derive that, and you'll see that it's actually not very complicated at all. All of the hard work for this, we've already done in chapter. Okay? All right, before we move forward, does anybody have any questions about these introductory concepts? Okay, I'm just investing a lot of time in framing the importance of this expression, even though the expression itself is not going to be very complicated. Okay? And it will actually resemble something that you guys have seen already in chemistry. All right, so let's see what the story is. Here. All right. So our starting expression is simply this, right? When you calculate the change in Gibbs energy for any point in the reaction, you just have to take the chemical potential of products minus the chemical potential of reagents. That's that. Okay, we're going to continue to talk about the reaction A to B, but we're going to make it a little bit more complicated by including stoichiometric coefficients, okay, which is not going to make it much more complicated. So suppose that now the reaction is A of A to give B of B. Okay, and again, lowercase a and lowercase b are just to make stoichiometric coefficients. It can be 1, or it can be 1 and 2, or it can be anything that you want in that. Okay? In this case, what you will actually have is that delta Rg, which is what you're trying to calculate here, is just going to be the stoichiometric coefficient of products, B, times the chemical potential of products, minus the stoichiometric coefficient of reagents, A, times the chemical potential of reagents. Notice that this actually is not very different from any state function that we have looked at in this semester, right? Entropy, what is the change in entropy in a reaction? Entropy of products minus entropy of reagents. What is the change in enthalpy in a reaction? Enthalpy of products minus reagents multiplied by the appropriate stoichiometric coefficients. Same thing, but in this case, this is Gibbs energy, and we're using here the chemical potentials. Now, what we actually know is that, again, this is going to have a dependence on concentration. But we actually have worked really hard in figuring out how that depends on concentration. And what we know is that this depends on concentration is this. Mu sub j is going to be mu sub j at the standard state plus RT natural log of A sub j. We know that, again, and that's the reason that we actually were working so hard in chapter 3 to do all this. Okay? Now we can actually use that to continue with this work right here. Alright, so let's see how this goes on. Delta Rg in that case is going to be equal to B times the chemical potential of B at the reference plus RT natural log of the activity of B.